Hello everyone. In this video, I want to focus on using the Descriptive Statistics data analysis tool found in Excel. I will be using Excel 365 for this. And the first thing you're going to need to know is actually how to download this tool because it is an add-in to Excel. First thing you want to do, and this is for PCs, is go to File, and you go all the way down to Options. You'll see that in this box that pops up on the left, as you scroll down near the bottom, you see Add-ins. So click on that, and then what you'll want to look at is at the very bottom of this, after you click the add-ins, you see down in the bottom, it says Manage Excel Add-ins, so you click Go. Next, this pop-up comes in with your add-ins. The Analysis Tool Pack, the very first one, is the one we want to use. If you have not downloaded this yet, you will not see this check. It will look like this, and you will want to check the Analysis Tool Pack. Once you have checked that, click OK. And where you will find it is on this top menu bar. If you go to Data, once you click Data on the far right, then you should see the Data Analysis tool. So this is a tool that we are going to be using in this lesson and focusing on. Now, before I actually get to that though, I want to show you one simple thing that you can do in Excel when you have data. So we're working with quantitative data now. So we have a list of numbers, numerical data. This represents pressure in pounds per square inch, or PSI, of 40 samples of concrete and the pressure they could withstand. So the pressure that could be withstood by 40 different samples of concrete in pounds per square inch, or PSI, is listed here. Notice I have a label in the first cell, A1, and then from A2 down through A41, I have my data. Now, if you just kind of look through this, skim through this, you should notice right away that this data is not in any particular order. It's just kind of all thrown in there randomly. So one of the most useful things to do first is to actually sort this data, meaning put it in a particular order. You can either sort it as ascending from smallest to largest, or as descending from largest to smallest. I am going to sort the data as ascending. So what I'm going to do is highlight all the cells that contain the data. Once they're all highlighted, then I'm going to go to Data, and here's the sort. And if I want to sort ascending, smallest to largest or lowest to highest, we use the A to Z. So sort A to Z, smallest to largest, and in the blink of an eye, everything is now sorted. So we see that our smallest value, or our minimum, is 2490.4, and the largest value, or maximum, is 2509.5. So there's our minimum and our maximum. We can easily see now, and then we can just kind of take a look and see how this is kind of distributed around. We notice, oh, there are a few repetitions. Look at this. Here's 2500.8 occurs 3 times. You know, we scroll down, we see a repetition here twice. Okay, so once we've done that, now we will go and do further summarizing using that data analysis tool that we just downloaded. We want to get the Descriptive Statistics tool because we want to look at our summary statistics. We're also going to later construct a confidence interval, so we at the same time are going to find the confidence level for the mean, and I will explain that later on. So let's first go to the Data tab, then the Data Analysis package, and the Descriptive Statistics tool. So here up on the top is data. Click it. Because we downloaded it, on the right you see data analysis. Click that. And then here's the data analysis with all the tools listed, and we are going to look at descriptive statistics. Click OK, and we get this pop-up. Input, our input range. This means where is the data? Grouped by columns or rows, our data is just in one column. And there's this box here that says labels in first row. I'm going to check that box because what that means is when I highlight or my input, the very first value in the input will not be a data value, but will be a label. So when we go back and look at our data over here, can't get to it, so let's do this again. So let me cancel and cancel. Make sure you can see your data. So let's go again. So that's data, data analysis, descriptive statistics. Okay, I click labels in first row because I am going to highlight the label that is in my first column, the first cell in the column, which is the first row. So make sure you're back in the input range box, and I'm going to highlight from A1 to A41. Notice here it puts it in $A, $1, colon, $A, $41. You could have typed in yourself A1 colon A41, not really even worrying about the dollar signs, and that would work just as well. Then we look at the output options. Notice the default is that it will put your output in a new worksheet, which means a new page will show up here. You'll see like sheet 1 show up. I want to keep it on the same page I'm working on, so I'm going to click output range to keep it on the same page. Now I click here in the input for that range, and I need to select where I want to put my range. Notice this time it's letting me scroll around. So I want to put it where I won't override anything else. I have some notes in here. I don't want to override the notes, so I think I will input it, let's say, let's put it to the side of the notes. So I'm going to have my output way over here in what looks like starting with column V. Yeah, let's try that. So let's put it here. Notice I only have to click what is going to be the upper left corner of the output. I don't have to click all the cells it will fit in. So it's going to start in V1. And now I need to make sure what I want to come and show or to be part of my output. Of course, we want the summary statistics. That's the main thing we're looking at. But I'm also going to click confidence level for the mean because I want to use that later on to construct a 95% confidence interval. 95% is the default confidence level. So if you haven't played with it before, that should say 95. We aren't going to worry about these other two boxes. Notice, though, you could do descriptive statistics and get only the single output, confidence level for mean, or you could get all the summary statistics and not this. We'll get both. So when I click OK, here's my output. I'm going to widen this. Actually, I want to widen the left column so I can see what the outputs show. All right, so here's my data. Down here, you see that confidence level output, so I'm going to make it big enough to see all that. We will get to this at the very end. We are going to focus on some other things up here first. All right, so let's see. Actually, just because it will be easier to see here, I am going to move this over a little bit. I hope you don't mind, but I'm going to go ahead, highlight all this, do Control X. Notice how it does the kind of dotted bordering. And I'm going to bring it over here so it'll be closer to see next to my explanations for the different measures we're going to look at. So I'm actually going to put it over here, starting in R. Notice I've simply highlighted that cell. I can just hit enter and everything has moved over. Again, I need to open this up so we can see all the descriptions. Looks good. Didn't override anything. Now it's next to or closer to the things I want to talk about as far as the descriptions I've written here for you. So we get a lot of output. We have the mean, something called the standard error, median, mode, standard deviation, standard variance, kurtosis, skewness, range, minimum value. Remember, we had already seen that and pointed out the 2490.4 when we put it in order. We also see the maximum value, 2509.5, which we also saw when we put it in order. There. Then there's the sum of the data. I personally have not yet used this output, but apparently it's important for some things. So here's the sum of the data. The count, this is the number of data values that you have. So it's your sample size. This is like your small n, your sample size. So there's the count. And then here's this confidence level output, which I will explain later on. So when we're looking at our output, there are several particular categories we're interested in. So the first kind of output we're going to look at is measures of central tendency. Measures of central tendency. Measures of central tendency are ways of defining the middle. We can define the middle in different ways. Usually when you hear the word middle, you're thinking of the physical middle, or what we call the median. Okay, the median is the physical middle. So when you have your data set ordered, it'll be the value exactly in the middle. Now, if I had, for example, 41 data values, remember I have 40 because A1 here is a label. I have 40 data values. If I had 41 data values, I would remove the top 20, the bottom 20, and that middle one, which is actually the 21st data value, would be my median. I do not, however, have an odd number of data values. I have an even number of data values, 40. So when I scroll down, I see that the 20th and the 21st data values, which in here will be on the 21st and 22nd rows, these are the two middle numbers. So I don't have a single physical middle. I have these two numbers. So the physical middle would be the average of these. So the average of 2500 and 2500.2 would be 2500.1. So when we go back and look at our output for the median, indeed, we see the 2500.1. Now, suppose you wanted to find this median without having to go through the data analysis tool, or let's say you weren't able or didn't have it added in and downloaded. So what other way could you find the median without having to yourself find the middle or average the two middle numbers? Well, of course, Excel does have a formula for that. So you hit equals median, start typing it in, there it pops up. And you just tell it then the range of your data. I'm going to actually type it in instead of highlighting this time. So the range of my data is A2 colon A41. Now, what's interesting here is I started to write A1, and A1 doesn't have a value, it has a label. But notice when I enter, it just ignored the label. It goes, oh, that's not a data value, and just ignored it. So I actually could just write A1 to A41 or A2 to A41. And there's the 2500. So we do have the formula median to give us the median. So I'll kind of write this on the side to remind you that here's a formula and up here I will write formulas. So we are listing the individual formulas you could do if you just wanted to find some values individually and not have the entire output. So the middle that we usually think of is called the median because that's the physical middle. However, the most important or most used measure of central tendency is the mean. And the mean is simply the average that you have learned about ever since elementary school. So the mean, or the average, we sometimes refer to this. There's more than one type of mean. When you hear mean, you usually mean arithmetic mean, and it's the arithmetic mean that is literally the average that you're used to hearing about. So the arithmetic mean, which is the average, we know that you have to add all the data together and divide by how many you have. Well, down here, they did give us the sum of the data, and we know how many there are. So we could, if we want, compute the mean using this information equals the sum divided by how many there are, and we get this 2499.895. We come up here, boom, I'm like, oh yeah, there's the mean, 2499.895. There it is. Okay, so that's just what we get when we add everything up and divide by how much we have. Of course, if you wanted the mean by itself and you hadn't yet computed anything, you could use the formula mean. So if we go equals MEA, it's interesting, you find it's not there because it's actually listed under average. See, so you want to know the mean is the average. A1 colon A41, close parentheses, and boom, there it is again. 2499.895, 2499.895. The formula is average. The last measure of central tendency we're going to talk about is the mode. And the mode is the most repeated data value. You'll probably realize it's possible you'll have data values with no repeats at all, in which case there would be no mode, and the output here would be an NA, not applicable because nothing repeated. Here, though, we do have repeats. And look, it's that 2500.8 that we noticed when we were skimming through here. So that 2500.8, which we noticed here occurred 3 times, that indeed was the value that repeated the most. So we'll go ahead and just kind of highlight. So there it is, the value that repeated the most was 2500.8. On a histogram, you know, it would have the highest bar. Okay, well, is there a formula for mode? There is indeed. Now, the thing here is our data set, at least when we skimmed through it, there seemed to only be one value that repeated 3 times and nothing else that also repeated 3 times or more than 3 times. Well, the thing that repeats the most is our mode. So, of course, if there were something repeated more than 3 times, then 2500.8 would be it. But it's also possible that we would have had another data value, you know, something over here. Maybe if 2502 repeated 0.5 was 3 times instead of twice, then we would have 2 modes and it would be bimodal. You could even have 3 values repeated more than once, trimodal, but we just, at that point, once it's, you know, unimodal, which is 1 mode, no mode, bimodal, 2 modes, and then usually we just say, okay, multimodal when there's several modes. The thing here then with this output here, this mode output will give you only 1 repeated value, and it's the smallest one, basically the first one it encounters as it scrolls through the list from smallest to largest values. So it's possible, if you're just looking at this, that you have more than 1 mode, and that was just the smallest value of the mode. All right, well, what then formulas do we have here? Notice if you start typing mode, you actually have two different mode formulas. There's mode single, which is going to find you only one mode, and it would be the smallest valued mode. So if I type in A1 colon A41, it would give me the exact same output here. So that was mode single, SNGL. Okay, so mode single, and it only gives you the first one. But what if there were more than one mode and you wanted to find them all? You would use mode Mult. Mode Mult. So over here, equals, start typing mode, and you see here there's that mode Mult. This would tell you if there were more than one mode. We know on ours there is not, so I'll show you what that looks like. So A1 to A41. Okay, now if I hit enter, there it is, there's only one. Well, would it have put all of them there if there were more than one? Actually not. Let me show you up here where it says mode Mult. If I click on this FX, notice it brings up this table. It's kind of like, wizard input table. Notice here our output is in curly brackets like a set. If there were more than one mode, that it would show up here with different commas. But notice down here it says formula result. It just gives us one value. Okay, this is what shows up. Now, let me cancel this and go back to mode single, highlight on that, go up here, hit that little FX, and see, notice its output has no curly brackets. There's one mode, it's not a set. All right, well, if it were a set and consisted, of more than one, if it were a set that had more than one value, all right, how would we get it to output here? Well, you would need to output an array. So when you did this, A1 colon A41, you're not going to actually see my keystrokes. But if you Google this, you find out that in order to output an array, which means there's more than one output, you would have to simultaneously hold down Control, Shift, and Enter. So Control, Shift, Enter, that then would have given us more than one mode and filled up more than one cell, if there were more than one mode. Control, Shift, Enter. If you forget, Google it, how to output an array using Excel. For some reason, if you just hit Enter, right, like when we did this, if I just hit, come on, I guess I should double click in there. If I just hit this FX here, right, what am I doing? Let's cancel this. I meant to be on this here. Okay, so if I click that, all right, in order to output the whole array, if there were more than one, okay, you would have to do the Control Shift Enter. If you simply click OK or hit Enter, you get this formula result, the single value. All right. Okay, so those are the three measures of central tendency that are important: mean, median, and mode. There is a fourth one that's not used much. We actually aren't going to use it in this class, but it's the midpoint, which is halfway between the minimum and maximum. We're going to see midpoints later, but not in terms of the entire data set. So measures of central tendency. Okay, so here are our measures of central tendency. Actually, I am going to highlight these things, kind of do a color coding thing. So let's do our measures of central tendency, and then I can mark them up here as well. So the mean, the median, and the mode are our three measures of central tendency. Okay, well, what other types of measures are there? There are measures of variation. What the measures of variation do is they tell you how much your data is spread out, how much it's dispersed. So measures of variation you can think of as dispersion, right? How much it's spread out. So dispersion. I am going to have to merge that with it. Okay, I wrote dispersions. We just mean dispersion. Measures of variation or measures of dispersion. How much the data is spread out. Well, the first, easiest, most obvious way to see how your data is spread out is the range. And the range is simply the difference between your max and min. And oh look, range happens to be here on the same line. That was fortuitous. All right, so here's the range. It is the difference between your maximum and your minimum. So notice I can go equals the maximum minus the minimum. See, and there's my range. Just the difference between the max and the min. Very easy to compute, really obvious. It is not the most important measure of variation, however, because it's really only taking into account the extreme values, right? The very smallest, the very largest. What's happening in between? Maybe what's in between are all kind of grouped together, and these n values are more outliers. So it tells us then, the difference between min and max, how far it's spread out, but not really how it's clustering in between those. And that's why we prefer better measures of variation, the variance and standard deviation. Standard deviation is the best, but notice the standard deviation is defined as the square root of variance, so we start with the variance. Before I go there though, let's see, is there a formula for range? It seems so easy to compute, you wouldn't need one. And no, there's not. Okay. All right, so range. So let's now look at variance. We would like a measure of variation that does not rely on only the extreme values, but takes all the data values into consideration. All the data values into consideration. Well, how are you going to work with that? How are we going to think, how is our data spread about? How are we going to measure this? So what is done, what the variance does, is it ends up measuring, basically, here's the sample variance. Let me highlight it right now. What it does, it's going to measure how much things vary from the mean. How far are things varied from the mean? So we're going to look at an average distance from the mean, right? An average distance from the mean. Let's kind of take a look at what would happen here. So average distance from the mean. So that would say I would want to take all the data values, subtract the mean from those data values, and then add them up. So we could say the sum, right? And then you would divide, you would think then by the sample size. Okay, add them all up, divide by the sample size. Note, however, though, that x minus mean here, if x is smaller than the mean, you get a negative number. X is bigger than mean, positive number. If you had a perfectly symmetric, or at least fairly close to symmetric, if it were perfectly symmetric, like a probability distribution, if you looked at finding variances for probability distributions, for every negative value, there's a corresponding positive value, and this actually zeroes out, so you have no information whatsoever. You won't zero out on sample data because you're not going to have perfect symmetry, but it won't give you a good measure because you will be canceling some things out, and it'll show something much smaller than you really want to look at. Okay, so if we can't do just that, we need to figure out how to make x minus mean always positive. Depending on how much algebra you've had and how recently, you might think, well, why not do the absolute value? Absolute values make everything positive. And it's like, well, sure, why not do that? Well, if you do that, though, it is called the mean absolute deviation. It's not the variance. It's the mean absolute deviation. And that is actually not used often. I don't see it around much. I used it once in a chemistry class to look at our data because it's actually easy to compute if you have a small data set and you don't really need to understand statistics to do it. But it's not used often, and it's likely because the absolute value function is not, quote, nice when it comes to calculus and things like derivatives. Why is it not nice? Well, let's see. If you remember the graph of the absolute value function, f of x equals absolute value of x. For x values that are negative, whoops, that's not absolute value. For x values that are negative, the absolute value is positive. For x values that are positive, the absolute value is positive, right? The outputs are always positive. That's what the whole point of taking the absolute value of x minus mean was meant to do, make it always positive. So when you look at a graph, I'm going to go ahead and just sketch a quick one for you. If you look at a graph then, so this particular one, which is just the very simple absolute value function, and I'll go ahead and draw some, just some quick, that's no good. I want to draw just quickly vertical and horizontal axes. I'm not going to be able to do this very straight. All right, so here's my x and y axes. The absolute value function looks like a V. Okay, assume that I was able to draw a straight line here. Right? It's a V. Why is that not, quote, nice in mathematics? Well, right here, you got a corner, a sharp point. All right, a corner, sharp point. It's not smooth, it's sharp. That then does not give it desirable properties. The background for all these statistical values were computed and derived using calculus, which you don't need to know when taking a class, but that's where all the theory comes from. In calculus, you can't, quote, differentiate a corner. So you would prefer to have a curve where you could differentiate everywhere. So if we smooth it out to get something more smooth like this, again, not the best graph, but hopefully what you can see, what I'm trying to draw here, is a parabola. And the parabola, you might recall, is the graph of the squared function. So squaring makes everything positive, smooths it out, so it's a nice function mathematically. That means then what was done, instead of absolute values and getting a mean absolute deviation, what we find are squared differences. What we're going to do then is find the sum of x minus the mean quantity squared. We're going to find the sum of these squared differences. And then we're going to average out that sum. Okay, we're going to average out that sum. But you're going to see that when we're talking about sample statistics, we actually don't just divide it by n, and I will explain why. But know that we will need, when you compute the variance, what you're doing is finding basically an average of the squared differences from the mean. right? Now, since it's always positive, I could also say distances, an average of the squared distances from the mean. So this here is the first thing you would need to compute, the sum of the square differences. This is referred to as a sum of squares, right? Or SS. It's a sum of squares or SS. So if I come back over here, let's get rid of this. If I come back over here, oh, I got to get rid of that. I always forget. That is, let us clear all that little graph. Okay, so if I come back to the notes I've written over here, see, right down here, the sum of squares. So the sum of squares, SS, is a sum of squares, and it's x minus mean squared. So that's the sum of squares. When you look at this, if you're looking at the formula for variance, you see, okay, there's the sum of squares. Oh, but it's being not divided by n. It's not being divided by the count here. It's being divided by something called df. Well, what's df? df stands for degrees of freedom. Degrees of freedom in this case, n minus 1. This n is the count. To remind you of that, I can come over here and I can type in n. Whoops, I want a lowercase n to remind you that that's the count. So we see degrees of freedom, one less than the sample size. One less than the sample size. Well, why are we dividing by one less than the sample size to get an average, which we're calling our sample variance? Why that? Well, it's because of one very important idea, that smaller samples have greater variation. We divide the sum of squares by df to account for, and I'm going to highlight this in yellow because this is actually a really important concept. We divide the sum of squares by the degrees of freedom to account for the greater variation in small samples. I have another video about the t-distribution, and in the t-distribution, it is different for different sample sizes, and there is more variation in smaller samples. Let me just show you that quickly, because I actually have a graph here, t-distribution. What you'll see in this graph, and let me try to make it a little bit bigger, is what's in blue is the standard normal distribution, right? So when you look down here, you see we have 0 in the middle because the mean of the standard normal is 0, normal is 0, and the standard deviation of the standard normal is 1. So here's 1 standard deviation to the left, 2 standard deviations to the left, 3. 1 standard deviation to the right, 2 standard deviations to the right, 3. Okay, and we see that, oh, this t distribution is really close to the standard normal. It's just a little bit different, and it's different mainly when we see it doesn't go quite as high up. Remember, the area under both of these curves has to be 1. So what happens here is, because there's more variation in smaller samples, the tails here are thicker because there's more, it's more spread out, so we have thicker tails. Okay, if your tails are thicker but the area underneath has to stay the same as in the blue curve, well, it's going to have to get a little shorter. Though the smaller your sample size, the greater this little difference here. It doesn't seem like a big difference, but it is enough to be statistically significant, even though this is only sample size 10, right? You're not usually going to have sample sizes as small. Of course, when I put sample size 5 in there, that's quite noticeable. Notice, though, how it changes. Let's see, we had 10 already. Let's go back to 10, right? Tails getting closer together. I have to make this just a tad smaller so you can see the tails at the same time. Let's go to 15. See, getting closer. 20. Closer yet. Usually in textbooks they go, oh, by the time you hit 30, it's the same thing as the standard normal. And you see, okay, very close, but not quite. That was to make things simpler back in the days without high computing probability like computers and calculators we have now. So we don't usually worry about that anymore. 30 is important as far as the central limit theorem applying, but as far as being the same as the normal, we can just keep, we can just keep using the t-distribution, right? Go 40, and you'll see though visually, it's getting closer and closer. All right, so for different sample sizes, because there's more variation in smaller sample sizes. So this t-distribution is affected by your sample size because it's taken into account the smaller samples have more variation. Well, we want to carry that over into our sample variance, our measure of the variation in our sample, our sample. So to take care of that, we actually divide by this degrees of freedom n-1. Not a big difference. Notice subtracting 1 from a sample of size 20 and dividing by 19 will make a much greater difference than subtracting 1, say, from 60 and dividing by 59 instead of 60. So as you see, the smaller the sample size, the smaller the degrees of freedom, and therefore the larger the fraction is when you divide by the degrees of freedom, resulting in a greater variance. The larger your sample, the smaller difference in between subtracting 1 here. This won't make as much a difference between dividing by n and n-1, so the variance will not differ as much. More variation in smaller samples. Very important concept. More variation in smaller samples. Greater variation in smaller samples. This is like a mantra. Do not forget this. There is greater variation in smaller samples. So to make sure we have a more accurate, technically an unbiased measure of variation, we divide by the degrees of freedom. Biased means that your sample statistic is not truly centered around the true value, because like I said, if there's more variation in smaller samples, if you don't do the subtract 1, you're going to have a smaller variance than is really warranted to. You'll be underestimating the true variance in the sample. So to make it unbiased, so they're actually centered around the true variance, we have to have this little change here, this just slight little tweak to make things work more accurately. So that's why it's important it's a sample variance. If you're working with a population, the entire population, not just a sample, entire population, so that you don't have to do inferential statistics because you know everything there is to know, well, then you wouldn't have to divide by degrees of freedom because it's not an estimator. It is the true parameter, so you just divide by n, the population size, so you would get a slightly different value. So the sample variance will always be a little bit bigger than the population variance, and the difference between those things will be more noticeable for the smaller sample sizes. Because of that, you actually have two formulas for variance. Notice if I go equal and start typing variance, there's a var.p and a var.s. S stands for sample. var.s is the sample variance. So if I type in r.s, sample variance, A1 to A41, see, I get the exact same thing. All right, now though, if I do the population variance, var.p, population variance, this would be a parameter if you knew the entire population. And I do A1 colon A41. Look, see, population variance is smaller. Sample variance is always going to be greater than the population variance. And I do note that right here. The sample variance is always greater than the population variance, but the differences between the two will become smaller and smaller as the sample size gets larger. All right, so it's very important that if you were to use the formula for here, that you would want to use the sample variance formula. Okay, you want to use the sample variance formula. I'm using up a lot of space here. I'm just going to have to write it here. That'll get confusing. So, okay, how about this? Let's do it here. So this is going to be var.s. Let's put it there. var.s, sample variance. Okay, that's the formula. Sample variance, all right? We're not going to be using var.p in this class because we're only going to be working with sample data. All right. Now, what is wrong though with sample variance? How come we don't hear about variance as much as standard deviation? Why is the standard deviation actually the value we always hear about? Well, remember, you're computing variance using a sum of squares. We are squaring this difference. That means once you square, you're not in the original units anymore. You're in squared units. So well, for example, here we're doing everything in PSI, pounds per square inch. But now we have a variance that's in pounds per square inch, quantity squared pounds per square inch. Well, what does that mean? You can't, it's like, apples and oranges. It's not good to compare. And so what do we do to get back to our original units? Well, what would you think? You do the inverse of squaring by taking a square root. So we take the square root of the variance to get the standard deviation, and that's this right here. So I'll go ahead and show you that. So I'm going to be doing several computations here. How about first I show you that standard deviation. Again, you see a stdev.p, stdev.s. So A1 colon A41, sample standard deviation, boom, same value. However, if you did your population standard deviation, stdev.p, A1 colon A41, all right, notice, too small, right? It's again too small. This was too small, this is too small, all right, too small. So let me highlight this one here. All right, but I also want to remind you that this is simply the square root of the sample variance. See, and there's the same value. All right, and that is always true no matter what kind of data you're working with, that a standard deviation is always the square root of the variance. And the variance is the sum of squares, so it's the sum of the square differences from the mean divided by degrees of freedom, which is one less than the sample size. So those are the primary measures of variation. So I've talked about the measures of central tendency and the measures of variation. There are still two things to talk about here, kurtosis and skewness. I'm going to go ahead and talk about those in a separate video so this one doesn't get too long. So if you're interested in what these are, right, these sound interesting. What are they? Skewness, kurtosis, you don't hear about that as much. What are those? I will talk about that in the next video. So I hope this video was useful, right? You know how to sort your data. You know how to get the data analysis tool, find your summary statistics using the Descriptive Statistics tool from your data analysis package. I've described most of the output, as in the measures of central tendency and the measures of variation. If you're running about this standard error, we'll be talking about that when we talk about confidence intervals, because that's related here. So we've talked about our measures of central tendency, our measures of variation, the importance of the difference between dividing your sum of squares by degrees of freedom to get a sample variance, to take into account the fact that there is more variation in small samples, greater variation in smaller samples, and so the sample variance will always be greater than the population variance. So you need to make sure that you're computing and using sample variance when you are working with sample data. Again, thank you for watching. I hope this was useful.